In this example, we're going to use stoichiometry in order to find out how much carbon dioxide is formed when butane burns. What we're going to do is we're going to first balance the combustion reaction for butane because we need to know the stoichiometry of the reaction. So in order to balance the combustion reaction, we'll start by writing the reactants and products of combustion. So our reactant is butane, C4H10. So we'll start C4H10, and of course in combustion the other reactant is always going to be oxygen. And since it's burning in the air, there's going to be enough oxygen for the reaction to take place. So we assume that there's excess oxygen. The result of this combustion is that we form carbon dioxide and water. Now, when we balance these reactions, we want to start and work from left to right so that we balance our oxygen last. So what we're going to do is we're going to start with the carbon. There's 4 carbons in each butane molecule, so that means that we're going to end up with 4 CO2s because each carbon dioxide has 1 carbon. So now we have 4 carbons on the left and 4 carbons on the right. Also in the reactants, in butane, there are 10 hydrogens. That means we need to have 10 hydrogens in the products. Water is the only product that has hydrogen, so we'll balance the hydrogen there. Each water has 2 hydrogens. We need to have 10, so we want to have 5 waters. Now we can go about balancing the oxygen. If we analyze the oxygen in the products, we have 2 oxygens in each carbon dioxide. There's 4 carbon dioxides, so we have 8 oxygens from the carbon dioxide. In the water, there's 1 oxygen in each water, so we have 5 oxygens from the water. So that means in the products, in total, we have 13 oxygens. Now, if we look back at the reactants, our oxygen only comes as diatomic oxygen. That means it comes in 2s. There's no way to come in 2s and get to 13. So that means because we have to have an even number of oxygens in the reactants and an odd in the products, we need to double everything so that it can be even in both the reactants and the products. So we're going to multiply the entire reaction by 2. Now we haven't yet put any number here, so when we multiply it by 2, we're still going to leave that blank. So we multiply this by 2, which means we have 2 butanes. We have some number of oxygens that we don't know yet. We have 8 carbon dioxides because we're doubling it. And we have 10 water molecules because we doubled that. Remember, when we balance, we can always adjust the coefficients, but we cannot adjust the subscripts. So now we can balance our oxygen. From the carbon dioxide now, we have 8 times 2, so we have 16 oxygens. From the water, we have 10 waters, so that means that there are 10 oxygens. And that means that we have a total of 26. We need to have a total of 26 oxygen atoms. They come in 2s, so we need to have 13 oxygens. So now we have a balanced reaction for the combustion of butane. 2 butane molecules, 13 oxygen molecules, 8 carbon dioxides, and 10 waters. Now that we know the balanced chemical equation, we can use stoichiometry to determine the number of grams of CO2 that will be produced when some number of grams of methane burn. Just like in the examples of converting grams to moles or moles to grams, we're going to start with what we have. And our general procedure is going to be that we start with the grams of C4H10. we convert to the moles of C4H10. And once we have our moles of our reactant, we can convert to moles of product, which in this case is going to be moles of CO2. And then finally, we will convert those moles into grams of CO2. So our strategy is to go from grams to moles, then use the balanced chemical equation to go from moles of reactant to moles of product, and then finally we can convert those moles into grams. So let's start with what we have, which is 68.4 grams of butane. Now, we're going to do a conversion from grams to moles, which means we want this to be in moles of butane. So we're going to put what we want, which is moles of C4H10, over what we have, which is grams of C4H10. For every 1 mole of butane, we have 58 grams. And that comes from our molar mass that I gave you. The next and the grams of butane will cancel. So now we have moles of butane. The next conversion that we're going to do is to go from moles of butane to moles of CO2. So what we want is we want to end up with moles of CO2. What we have is moles of butane. We use the balanced chemical reaction in order to figure out the ratio between carbon dioxide and butane. For every 8 molecules of carbon dioxide, we have 2 molecules of butane. Our moles of butane, which is what we have, cancels, and now we have moles of CO2. Finally, we want to convert from moles of CO2 into grams of CO2. So what we want in this case is grams of carbon dioxide, and what we have is moles of carbon dioxide. We're going to use the molar mass of carbon dioxide in this case, where 44 grams is equal to 1 mole. The moles of CO2 cancel, and we're left with grams of CO2. So when we do the math on this, what we find is that we end up with 207.6 grams of carbon dioxide. The math on this is that we multiply 68.4 times 8 times 44, and that number gets divided by 58 and also divided by 2. Be sure that you can get this number when you do that math on your calculator.